Okay, thanks everyone for coming. I will be presenting saliency deficit and motion outlier detection in animated scatterplots. My name is Rafael Veras. So in data visualization, we map data variables to visual variables. And we combine these mappings in multidimensional plots. So with this strategy, instead of having to create many plots with little information, we can create a few plots that contain a lot of information. And then we can rely on our vision to extract only the information that we need to answer a given question. But for this to work, we need to be able to pick one or two variables and analyze them independently from other variables. For example, in this plot, we can see that size increase from left to right. And it's very easy to observe this dependency. But if we introduce another variable and map it to vertical position, this relation becomes a little bit less clear. And it becomes a lot less evident if we introduce a color mapping to this plot. And that's because color interferes with our perception of size. So to be able to ignore color requires a little bit of extra work. So these kinds of interactions between visual channels and how they impact task effectiveness is the topic of our paper. In particular, we focus on motion in animated scatterplots. So the animated scatterplot is a great plot to study this kind of effect because it can hold many variables. And the more variables, the more opportunities for interference between the visual channels. So we observed that in these plots, the points that stand out are those with a unique size or color, those that move outside of the point cloud, or those that move in unexpected directions. So for instance, in this sequence, the highlighted points are likely to stand out. So China because it's large and moves along the edge of the point cloud, and the other countries because they move into open space. But there are points that go unnoticed, even though they move faster than the others. So Emirates here is one of these points. It's inside the point cloud, and it's small, so it doesn't attract much attention. So that leads us to hypothesize that motion saliency in these plots must depend on visual features like size, color, and position. So more formally, we want to find which dimensions, if any, influence our perception of motion. Are these dimensions misleading? So if I ask you to find the fastest point in a plot, are you more likely to miss it because it's in the middle of the point cloud? So this question is important because the answer can determine whether or not we can rely on animated scatterplots to find certain kinds of information. So pay attention here to how we decompose motion into speed and direction. So in this paper, we treat these properties separately. So we present a user study to answer this question. And we frame it around the task of motion outlier detection. So here's a speed outlier, which you can easily see if you plot the speed distribution of this plot. So our strategy then is to present the outlier in a multidimensional plot and manipulate its visual properties while keeping motion constant. So here's the same outlier in a multidimensional plot. So here we vary color, direction, and size. And we present it with average features. So it has average color, average size, and average direction. And here's the same point presented with salient features, with more salient features. So it has a more salient color, more salient size, and is moving in a more salient direction. So we can measure if these changes influence people's ability to find the target. And we can do the same thing for direction outliers. So we have direction outliers presented with average and with salient features. So in order to manipulate the saliency of the target, we sample values from normal distributions. So when we need the target to have an average visual property, we pick the mean of the distribution. When we need the property to be salient, we pick the maximum value from the sample. So the outlier is always a value outside of the sampled range. So we created these plots by simulation, and we split them into two groups. So the first group contains average targets with low visual saliency. So there's a baseline where the target has no salient features, and then 5 variations where we turn on one salient feature. So here is position, salient direction, size, color, and delta size, which is the growth between the size growth between the two frames. And the other group contains salient targets. So we have a baseline where all visual dimensions are salient, and 5 variations where a single dimension is average. So here's the baseline, and then we turn off position. Here is presented with average direction, average size, average color, and average delta size. And this is the overview of the experimental setup. So we have an average group and a salient group, and each has 6 conditions. So in total, we have 12 conditions. And in addition to that, we created 10 scenes. So for each of these scenes, we manipulated the target according to the 12 conditions that I described earlier. So what you see in this display is 10 scenes where the target is in the baseline salient condition. So this introduced variation to the experiment, right? Replication. And this is the task page. So participants were allowed to play the animation up to 3 times before they selected the target. Before they selected the target and submitted the task. So here are some numbers about this experiment. So we had 2 tasks, to find the speed outlier and to find the direction outlier. So for each task, we had 10 plots. And for each plot, 12 conditions, 12 target conditions. So in total, we had 240 stimuli, and we collected 20 judgments per stimuli for a total of 4,800 observations. And we deployed this on Mechanical Turk, and we had 67 participants completing these tasks. So let's see the results. And let's start with speed. So the median accuracy in the average baseline was approximately 23%. So that's when the target does not have any salient features. If you present the target out of the point cloud, the median accuracy jumps to over 50%. Increasing the size of the target didn't help much. And presenting the outlier with salient color seemed to help a bit. And when the outlier moved in a salient direction, the effect was similar to that of having salient position. Increasing the size growth between the frames did not help. Okay, so now let's see the salient group. So the baseline, where the target has all features salient, achieved a much higher accuracy, around 80%. And turning off salient features did not cause much drop in accuracy. With direction, we see a similar pattern. So the baseline in the average group had low median accuracy too. And here, position and speed made a difference, but not so much the other variables. So when the target was all salient, the accuracy was over 50%. And again, we see this consistent effect of position and speed. The accuracy dropped when the target was inside the point cloud, or had average speed. So we fed logistic regressions to this data. So this model basically takes all the visual properties of the outlier and outputs a probability of correct detection. So it learns the influence of each variable on the odds of correct detection. So from this model, it's clear that spatial dimensions have the most impact. So here, direction and position for the speed task, and position and speed for the direction task. So our analysis showed that data outliers did not always correspond to visual outliers. For this reason, we state that motion outlier detection is unreliable in animated scatterplots that present many variables. So to explain this failure, we use the term saliency deficit, which we define here as a condition of imbalance between data and visual importance due to lack of saliency. And we characterize this as a violation of the principle of visual data correspondence from Kendallman and Scheidegger. So this principle states that important changes in data should yield salient changes in the visualization. So what does this mean in practice? Well, in plain terms, we asked participants questions about motion outliers, and half the time they were more likely to get it wrong. So we conclude that the animated scatterplot is not the best choice if the user needs to make accurate judgments about motion or discover motion outliers. And we encourage designers to consider alternative representations. So it's important to point out the limitations of this experiment. So first, we had a fixed value for outlierness. It's quite plausible that beyond a certain level of outlierness, there's probably no saliency deficit. Second, our scale ranges were informed by common practice. So you can see, for example, that we use the Veras color map. But the design space is huge. So, for example, with a different color map, we could get more or less visual saliency. So the effect of color may have been underestimated. And we also tested outlierness in a single direction only. So all the outliers had much higher value than the average. So in summary, we manipulated the saliency of motion outliers and we measured detection rates. And we find that motion outlier detection is influenced by features that are irrelevant to the task. And we conclude that non-salient motion outliers can be hard to detect in animated scatterplots. So we invite you to read the paper, and there you will find much more information. Besides all the technicalities, there's an analysis of the patterns in wrong selections, analysis for the number of replays, and much more theoretical discussion. Thanks, and I'll invite questions now.
Questions? Again, please state your name and affiliation. Oh, the microphone's, yeah.
So, Keith Andrews, Graz University of Technology, Austria. Great talk, thank you. Hans Rosling, when he's giving his performances, he already knows what he wants to say. Like, he's already detected the outliers, and he tends to sort of highlight them with labels or outlines in red so that the audience can see them. And I think maybe what you're getting more at is not the presentation of the result, but for the analyst during the analysis phase. Is that right?
That's correct.
So for people making scatterplot visualizations for analysts, we shouldn't rely on motion is the basic message, right?
That's correct. So
perfect.
For general purpose, if you want to enable discovery of motion patterns, not all motion patterns. So we're dealing, the scope here is motion outliers, right? Then it may not be the best option. But it's important to point out that we tested up to 3 replays. So participants had the opportunity to see the visualization 3 times. So it's possible that if you see 10 times, maybe you will get the right answer. So the guideline is if you need fast and accurate discovery of emotional outliers, then it may not be a good choice.
Perfect, thank you.
Hi, Tim Harrison, DSTL. Really interesting work. I'm just curious, the animations you used were like about a second long.
Right.
And irrelevant to the fact that they did get replays, have you thought about looking at things where there was either the animation took longer, so they had more chance proceedings, and or just longer, maybe at the same speed, but longer duration things? Because there's quite a short thing, so I'm just wondering if it applies to other things.
So there are several reasons why we did it short. So first, we wanted the best chance to actually detect an effect. If we made it too easy, it would maybe there was a chance that we wouldn't detect the difference because the task was too easy, and then it wouldn't matter. But the other thing is that you see we only have 2 frames, and these animations are quite long. So they are played in the context of, for example, the Gapminder data. There is so you're seeing the yearly indicators of countries from the 1900s to 2000. So in that long sequence, there is a huge number of these 2-frame transitions. And so in practice, they are played really fast, these 2-sequence transitions between states. So it's also for ecological validity.
Can I ask a follow-up on that? Is it?
Yeah, sure.
Just since you're now saying it's representative of that part in a longer animation, have you done anything where you looked at these things happening within that longer animation and whether people can pick it up within this, or whether it requires that it is this isolated bit that enables that detection?
We didn't, but we do have a hypothesis for what happens. It seems like if your eyes are caught by some of these outliers, they're really salient, you may actually miss a bunch more outliers because, I don't know, it's your attention is focused on one outlier, and then it takes a while for you to release, for that mechanism to release. So I think if this study is done with eye trackers, you may be able to get more insight into what kinds of things happen. What's the actual visual mechanism?
So we have time for one more question while we're switching. Did you?
Hi, Samantha Stalkey, Ontario Tech. In your future work, are you looking at maybe using the predictor model that you had for assessing the probability of misdetection as, say, a tooltip that kind of users could turn on and then, say, have a range of, I want to see any outliers that have over a 50% chance of misdetection, and kind of finding that balance between how much additional information you'd be giving them if you, say, flagged the points by pinging an animation on them versus kind of the information gain they'd be getting just by having those additional points that they might otherwise miss?
Yeah, this was actually the original idea. We wanted to have a model that would predict when the outlier was going to be missed, and then kind of like bump the saliency of the outlier by using trails or something like that. So yeah, that's quite an opportunity for future work. Thanks.
Great. Let's thank Rafael again.